Imagine that we have a spaceship, not a magical science fiction machine, but a real spacecraft built with technology we understand today. With this remarkable spacecraft, every planet in our solar system becomes a possible destination, transforming the impossible. But one fascinating question remained. How long would it actually take to visit every single world that circles our sun? The answer is far more complicated than it first appears, because every journey through space is shaped by the relentless forces of gravity and orbital motion. Before beginning our incredible voyage, we first need the most reliable map imaginable, one capable of, unlike any map on Earth, this one cannot measure simple straight-line distances, because nothing in the solar system ever stands still.
Every planet is constantly racing along its own orbit, making the entire solar system a magnificent dance of continuous motion.
At this very moment, Earth is hurtling around the Sun at more than 107,000 kilometers. When we travel toward Jupiter, we never aim for where the planet is now. We carefully calculate where it will be when our spacecraft finally arrives. It is much like trying to hit a moving target, while both you and the target are racing through space at extraordinary speeds. Every major mission usually allows only one perfect opportunity, making each maneuver incredibly important. Missing the target could mean losing years of planning, priceless scientific discoveries, and an entire mission. The greatest limitation of every journey through space is fuel, the precious resource that determines everything we can accomplish. Every kilogram of fuel must be used with extraordinary precision, because there is almost no room for waste.
Even one inefficient maneuver can consume valuable fuel and dramatically reduce our chances of reaching the intended destination.
Every voyage across the solar system demands patience, precision, and constant respect for the unforgiving laws of physics. To travel efficiently, we must learn to work alongside gravity instead of constantly fighting against it. Before gravity can become our greatest ally, we must first overcome Earth's powerful gravitational grip. Escaping Earth's gravity requires more energy than any other stage of our journey through the solar system. During launch, our rocket consumes an astonishing amount of fuel every second simply to overcome Earth's immense gravitational pull. At last, we leave the atmosphere behind and officially enter the vast emptiness of outer space. Now safely in orbit, our spacecraft races around Earth at extraordinary speed while gravity continuously bends our path into a graceful circle. Although it feels as though we are traveling in a perfectly straight line, gravity is constantly shaping every moment of our flight. Instead of steering like an aircraft, our spacecraft naturally follows the invisible curve created by Earth's gravity. With our understanding of orbital mechanics growing stronger, we are finally ready to leave Earth behind and begin our unforgettable voyage across the solar system. The harder our engines push against Earth's gravity, the straighter and farther our orbital path stretches into space. If we slow down instead, Earth's gravity bends our flight path much more sharply, keeping us closer to our home world. If our orbit curves too much, we risk falling back toward Earth on a fiery collision course that ends our journey before it truly begins. To avoid that fate, we dramatically increase our speed until Earth's gravity can no longer keep us bound. This tremendous burst of velocity finally allows us to escape Earth's gravity and begin our true interplanetary voyage. Relative to the Sun, our spacecraft now races through space at nearly 150,000 kilometers per hour. We have become another independent traveler orbiting the Sun, following the same universal laws as every planet and moon. Although we escaped Earth, the Sun's overwhelming gravity still firmly holds us within the solar system. Because nearly every major planet shares the same orbital plane, our journey is largely defined by traveling either toward the Sun or away from it. No matter which direction we choose, gravity ensures that our route always bends into elegant curves instead of perfectly straight lines. Just as we controlled our orbit around Earth, we guide our path through the solar system by carefully increasing or decreasing our speed. While wandering through space might seem simple, reaching a specific planet demands extraordinary mathematical precision and flawless timing. With our navigation complete, We now set our course for the first planet from the Sun, the mysterious world of Mercury. Surprisingly, Mercury is the most difficult planet in the entire solar system for us to reach. Mastering a journey to Mercury prepares us to understand nearly every other challenge awaiting us across the solar system. Although Mercury appears relatively close to Earth, its position deep within the Sun's gravity makes the journey far more demanding than simple distance suggests. Orbiting only 58 million kilometers from the Sun, Mercury moves at extraordinary speed to avoid falling inward.
Mercury circles the Sun at nearly 170,000 kilometers per hour, making it an exceptionally fast-moving destination.
To reach this swift planet, we must overcome two enormous challenges involving both our speed and our trajectory. First, we deliberately reduce our speed so the Sun's gravity can begin pulling us toward Mercury's orbit. Our greatest challenge is controlling this fall carefully enough to arrive beside Mercury, instead of racing uncontrollably past it. Success depends on reaching Mercury at exactly the right speed, so its gravity can safely capture our spacecraft. From Earth's orbit, we intentionally sacrifice much of the speed we worked so hard to gain during our escape. By allowing the Sun's gravity to reshape our trajectory, we begin a carefully controlled descent toward the innermost planet. Our long descent toward Mercury has only just begun, and the most demanding phase of the journey still lies ahead. Surprisingly, falling toward the Sun is actually the easiest part of reaching Mercury, although every moment consumes more of our precious fuel. Descending into the Sun's gravity is much like rolling a massive boulder down a steep mountain, where every second naturally increases your speed. At first, our descent feels gentle, but the closer we move toward the Sun, the faster gravity relentlessly accelerates our spacecraft. The Sun's immense gravitational pull becomes stronger with every passing kilometer, transforming our careful descent into an extraordinary rush through space. Even though we slowed down earlier, gravity now accelerates us far beyond our original speed as we approach the inner solar system. This tremendous acceleration helps us catch Mercury, but it also creates our next and most dangerous challenge. By the time we reach Mercury's orbit, our spacecraft is traveling at an astonishing speed of more than 210,000 kilometers per hour. At this incredible speed, we desperately need to slow down, or we will simply fly straight past our destination. This exact challenge once confronted an early NASA mission that successfully reached Mercury, but could never remain there.
Arriving in only a few months came at a cost because the spacecraft traveled far too quickly to enter orbit around the planet.
Instead of staying, the mission gathered as much valuable scientific information as possible during its brief encounter before disappearing into deep space. In theory, we could slow ourselves using our engines alone, but doing so would require an unrealistic amount of fuel. Fuel limitations have always been one of the greatest obstacles preventing long-term missions to Mercury. Eventually, a remarkable spacecraft proved that reaching Mercury safely was possible through an entirely different strategy. Instead of carrying impossible amounts of fuel, the mission relied on gravity itself to reshape its journey. Although this method dramatically reduced fuel consumption, it required years of carefully timed planetary encounters. Our first major destination on the road to Mercury is not Mercury itself, but the mysterious world of Venus. We intentionally approach Venus so its gravity can naturally redirect our spacecraft toward a more favorable path.
By passing close enough, Venus gently bends our trajectory without requiring large amounts of fuel from our engines.
This remarkable maneuver is known as a gravity assist, allowing the planet itself to perform much of the difficult work.
After looping around the Sun, we meet Venus again for another carefully planned encounter. Flying extremely close allows Venus's gravity to reshape our course even more dramatically than before. These repeated gravitational encounters gradually prepare us for our first close approach to Mercury. Each encounter with Mercury gently adjusts our speed until our spacecraft nearly matches the planet's own orbital motion. At last, After years of careful planning and gravity-assisted navigation, one perfectly timed engine, we ignite our engines at precisely the right moment, allowing Mercury's gentle gravity to capture our spacecraft into a stable orbit. Although Mercury's gravity is only about 1/3 as strong as Earth's, it is powerful enough to hold us if our speed is perfectly controlled. When every calculation succeeds, Mercury's gravity overcomes the Sun's pull just enough to keep us permanently circling this remarkable world. Even with an advanced spacecraft and perfectly executed gravity assists, reaching Mercury safely requires nearly 5 years of careful navigation. Fortunately, not every journey through our solar system demands such extraordinary patience and complexity. Our attention now turns toward Venus, Earth's closest planetary neighbor, and the shortest major voyage beyond our home world. Even though Venus is our nearest planetary destination, the journey still presents fascinating technical challenges that demand precise navigation. Beginning our voyage to Venus requires slowing down just enough for the Sun's gravity to guide us inward. As we begin falling toward the Sun once again, gravity naturally accelerates us along the perfect path toward Venus. Within only 4 months, our spacecraft reaches the orbital highway traveled by Venus. Just as with Mercury, we arrive moving far too quickly to be captured naturally by the planet's gravity. Unless we reduce our forward velocity, we will simply continue flying past this beautiful neighboring world. Fortunately, Venus offers significant advantages that make entering orbit much easier than around Mercury. Venus is much larger than Mercury, giving its stronger gravity far greater ability to bend our path and capture our spacecraft. Even more importantly, Venus possesses an atmosphere almost 100 times denser than Earth's. By barely touching the upper atmosphere, aerodynamic drag naturally removes enormous amounts of speed without consuming additional fuel. Combining atmospheric braking with one carefully timed engine burn allows us to enter orbit around Venus in less than 5 months. Our next destination changes the entire nature of the journey, because Mars lies farther from the Sun instead of closer. Instead of descending into the Sun's gravity, we must now climb away from it toward the cold outer reaches of the inner solar system. Fighting against the Sun's gravity makes every kilometer outward more demanding than falling inward toward Mercury or Venus. Reaching Mars has become one of humanity's greatest achievements, with many successful missions following this route across the decades. The most efficient journey uses a carefully calculated Hohmann transfer orbit that minimizes fuel while maximizing precision. We patiently wait until Earth and Mars align in just the right positions, an opportunity that arrives only once every 2 years. During this brief launch window, a carefully measured burst of speed begins our long climb toward the red planet. Our voyage to Mars has begun, and the challenges of slowing down on the far side of the Sun are only just beginning. That carefully measured burst of speed is just enough to lift our spacecraft outward toward the orbit of Mars. Although we could reach Mars much faster by burning more fuel, doing so would create an even greater challenge when it comes time to slow down. Because Mars travels much farther from the Sun than Earth, it moves around our star at a significantly slower orbital speed. By the time we arrive, our tremendous speed must be carefully reduced to match the much slower motion of the red planet. Our spacecraft must slow from nearly 150,000 kilometers per hour to a speed that Mars can successfully capture. Unlike our voyage toward Mercury, there are no nearby inner planets waiting to provide a helpful gravity assist. Mars also lacks the dense atmosphere that allowed Venus to slow our spacecraft through gentle aerodynamic braking. Because Mars possesses weaker gravity and only a thin atmosphere, our engines must perform nearly all of the work required to slow down. This dependence on powerful engine burns is why a safe journey to Mars typically requires nearly 8 months. After months of careful navigation, we finally settle into orbit around one of the most fascinating planets humanity has ever explored. Beyond Mars, our journey becomes even more extraordinary as we prepare to enter the vast outer solar system. Jupiter lies nearly 5 times farther from the Sun than Earth. making it one of the longest journeys we have attempted so far. The enormous distance means we cannot simply move from one nearby orbit to the next, as we did when traveling between the inner planets. Once again, gravity becomes our greatest ally as we prepare to use planetary motion to reach Jupiter efficiently. Earlier, we used gravity to descend toward the Sun, but now we use it to fling ourselves outward into the distant reaches of the solar system.
Once we are moving outward, two enormous challenges stand between us and the giant planet ahead.
The first obstacle is crossing the famous asteroid belt, a vast region filled with countless rocky objects orbiting the Sun. This immense zone contains everything from tiny grains of dust to gigantic rocky worlds hundreds of kilometers across. Even a collision with a relatively small rock could cause catastrophic damage when both objects are moving at enormous velocities. Despite what movies often suggest, the asteroid belt is mostly empty space, making dangerous collisions surprisingly unlikely. In reality, a spacecraft can usually cross this enormous region without ever coming close to another asteroid. Beyond the asteroid belt, an entirely different challenge awaits us: the overwhelming presence of Jupiter itself. Jupiter is truly colossal, containing more mass than every other planet in the solar system combined.
Its extraordinary gravity reaches far into space, dominating everything that ventures too close.
As Jupiter's gravity pulls us inward, our greatest challenge is no longer getting there. It is finding a way to slow down before Jupiter's powerful gravity now begins drawing us inward, transforming our steady climb through the solar system into another rapid descent. Just as the Sun accelerated us toward Mercury, Jupiter now dramatically increases our speed as we approach its enormous gravity well. Far from the warmth of the Sun, everything moves through space at a much calmer and slower pace than in the inner solar system. While Mercury races around the Sun at incredible speed, Jupiter travels along its distant orbit at a much more relaxed pace. Even after traveling for years, our spacecraft is still moving far faster than Jupiter itself, creating another difficult braking challenge. Jupiter's immense gravity is both an extraordinary advantage and one of the greatest obstacles any spacecraft must overcome. Fortunately, Jupiter's gravity naturally bends our path into orbit even before we have fully matched the giant planet's speed. Instead of eliminating all of our speed, we only need to slow down enough for Jupiter's gravity to permanently capture our spacecraft. When NASA's Juno spacecraft arrived at Jupiter, it performed a precisely timed engine burn lasting more than half an hour to safely enter orbit. Every second of that carefully controlled burn determined whether the mission would succeed or disappear forever into deep space. After years of travel across the solar system, we finally settle into orbit around the largest planet ever explored by humanity.
But what if we choose not to slow down and instead continue racing past Jupiter into the unknown?
By refusing to let Jupiter capture us, we unlock an entirely new method of exploring the outer solar system. Jupiter's enormous gravity now becomes a powerful slingshot, redirecting our path toward even more distant worlds. Instead of capturing us, Jupiter redirects our tremendous momentum towards Saturn with remarkable efficiency. The incredible speed we gained during our long journey now carries us naturally toward the ringed giant waiting farther from the Sun. Ahead of us lies Saturn, one of the most beautiful and recognizable planets in the entire solar system. Saturn's spectacular rings create one of the most astonishing sights any spacecraft could ever witness. Every kilometer closer reveals extraordinary details hidden within the vast structure of Saturn's icy rings. The rings are not solid structures, but countless pieces of ice and rock gracefully orbiting the giant planet. Beyond the rings, an extraordinary family of icy moons circles Saturn, each one offering remarkable opportunities for future exploration. Among Saturn's many moons, Titan stands out as one of the most fascinating destinations anywhere in our solar system. Yet our incredible journey does not end at Saturn, because even more distant worlds await us beyond the ringed giant. Every successful gravity assist carries us farther from home, deeper into the vast frontier that stretches beyond the familiar planets. Our next destination lies even farther from the warmth of the sun, where the frozen worlds of the outer beyond Saturn, every destination grows dramatically farther apart, turning each new voyage into a journey measured in years rather than months. Our next destination is Uranus, an icy giant that orbits nearly twice as far from the sun as Saturn itself.
Unlike the colorful cloud bands of Jupiter and Saturn, Uranus presents a calm blue appearance shaped by methane high within its atmosphere.
Reaching Uranus efficiently depends on using the momentum we gained from the giant planets, rather than carrying impossible amounts of fuel. As we continue outward, sunlight grows noticeably weaker, leaving our spacecraft surrounded by a colder and darker frontier. Even after traveling for years, Uranus remains one of the most mysterious worlds ever visited by a spacecraft. A carefully timed engine burn allows Uranus to capture our spacecraft into a stable orbit around this distant icy giant. From orbit, we discover a quiet and frozen world, unlike any other planet in our solar system. Uranus is unique because it rotates almost completely on its side, giving the planet some of the strangest seasons imaginable. Leaving Uranus behind, our voyage continues toward the final major planet in the solar system. Neptune waits billions of kilometers from Earth, making it one of the longest planetary journeys we can undertake. Despite receiving only a tiny fraction of the sunlight Earth enjoys, Neptune remains a remarkably active and dynamic world. Neptune's atmosphere contains some of the fastest winds ever measured anywhere in the solar system. After years of travel through deep space, every maneuver becomes increasingly important as we prepare to enter orbit. One perfectly timed engine burn allows Neptune's gravity to gently capture our spacecraft into orbit. From orbit, Neptune reveals a breathtaking world of powerful storms, frozen beauty, and distant mysterious moons. Triton, Neptune's largest moon, may preserve clues about the earliest history of our solar system. Beyond Neptune, the familiar planetary family slowly fades behind us as we approach the edge of the known solar system. Ahead lies the Kuiper Belt, a vast region filled with frozen remnants left over from the birth of the solar system. Hidden among these icy objects are dwarf planets that continue to challenge our understanding of how planetary systems evolve. Pluto may no longer be classified as a major planet, yet it remains one of the most fascinating destinations in the outer solar system. Even at the edge of the sun's influence, Pluto reveals astonishing geological features that continue to surprise scientists. As we leave Pluto behind, we begin approaching the true frontier, where our solar system gradually gives way to interstellar space. Ahead lies the edge of the sun's protective influence, where our extraordinary journey